Remember, we're talking about transformations of functions, right? Meaning moving them around, changing the shape, flipping them upside down or right to left. And today we're going to talk about horizontal and vertical stretches. Vertical stretches you've seen before, horizontal stretches you have not, right? So a stretch, unlike a translation, remember translation means shift, changes the shape of the graph. A shift just moves it, it keeps the same shape. But a stretch, depending on whether it's horizontal or vertical, will change the shape. Now a vertical stretch, what we do is we take the shape and anything on the x-axis stays there because we stretch it from the x-axis. So like if I have something, don't copy this down. If I have something like this, right? And if I'm going to vertically stretch it, let's say I'm going to expand it, this stays the same. These get pulled, okay? Or another type of stretch is called a compression. If I stretch it down, again, this does not move, okay? So anything on the x-axis with vertical stretches don't move. Oops. So let's just review vertical stretches first. And we're going to use the graph y equals x squared, which you should be familiar would look like this if you graphed it. That's y equals x squared. Now remember, when we stretch it, if we pull it or push it down, okay, the x values are not going to change. It's the y values for each point that are going to change. This is going to get pulled up or pushed down, but it's still going to stay on this horizontal line x equals 2. Same with this, same with this, same with this. Okay, so the y values are affected in a vertical stretch, which makes sense because whenever you think vertical, think of a coordinate grid, the y-axis is always vertical. Okay, before I go into this, I'm going to go down here. So here are the points that I plotted when I, remember this was the one y equals x squared. So now I want to see what's it look like when I throw a number in front of the x squared. Either a big number, like 2 or 3 or 4 or 5, or a small number between 0 and 1, like a fraction. Okay? And we have seen what's happened last year, but I just want to review it here. So I'll use a different color. So remember, the x values are not changing. So when I create these two new graphs, all the x values are going to stay the same. So this is still going to be -2 for x, but y is going to change. This is still going to be -1 for x, but y is going to change, etc. And the same with if I stretch it by 1/2. Stays the same, bless you. And so on. Okay, let's look and see what happens to each point when I plug it in this function with a 2 in front. Okay. That means I'm going to go -2 squared, which is -2 squared times 2. So this becomes 8. And then do that for each of the x values, because remember, they don't change. So -1 squared is 1 times 2. That means this point would become -1, 2. 0 squared is still 0. 0 times 2 is still 0.
Plug in 1 squared times 2, I get 2. 2 squared is 4 times 2, I get 8 again.
What happened to every y value?
From here to here.
Pardon me? Divide by 2?
Multiply by 2. So that's what it looks like in mapping notation.
So if there's a times 2 in front of the function, in this case x squared, that means that we take every y value on the original point and double it.
So what does this look like on the graph? Well, this stays the same. The -1 and +1
Become 2.
And the -2 and the +2 become 8. So this is nothing new. That's y equals 2x squared. So after we do the vertical stretch, we get new points. Or you will commonly see this word, image points. So the image point from, let's say, 1, 1 goes to 1, 2.
Okay? The image point is the point on the new function after we've done the transformation to the original point.
So in 2x squared, each y value is double. And we call this a stretch by a factor of 2.
That's how you describe it. You must,
When you describe a stretch,
you must use that phrase, by a factor. Factor itself means multiplication. Okay, so when we talked about shifts, we say shift 2 left, shift 3 up. When we talk about vertical stretches, we say vertical stretch by a factor of 2. So we don't say vertical stretch 2 or vertical stretch 2 up. We don't say things like that.
so make sure you get your wording right.
Well, so what do you think is going to happen in a half x to all the y points? Yeah, they're going to stretch by a half, by a factor of 1/2. Each y value is going to get multiplied by 1/2.
And if we go down here and do it, we'll see that's the case. So remember, I'm taking -2, plugging it into here. So -2 all squared is 4. 4 times 1/2 is 2. -1 all squared is 1. 1/2 times 1 is 1/2. 0, 1/2, after I keep plugging all the original x values in, and 2. So what happened to each y value from its original point to its image point? We multiplied all the original y's by 1/2. What does that look like on the graph? Well, 0, 0 still stayed at 0, 0. -1, 1 became -1/2, 1. Or sorry, -1/2. 1, 1 became 1/2. 2, 4 became -2, 2. And 2, 4 became 2, 2. So we see we get a bit of a wider graph whenever the number in front, or the coefficient of the function, is a fraction between 0 and 1. He's saying it stretches, where it stretch by a factor of.
Right? This just makes sense, right? If there's a times 2 in front, we multiply all the y's by 2. If there's a times 4 in front, we multiply all the y's by 4. If there's a 1/7 in front, we multiply all the y's by 1/7. This makes, it intuitively makes sense. Something new that we didn't talk about last year, when you take an original function and create a new one by some transformation, sometimes points don't move. Original points don't move. Going back to this, was there a point or points that did not move when you did the stretches? 0, 0. Those kind of points we refer to as invariant points. They didn't change. So in y equals 2x squared and y equals a half x squared, the invariant point was, or is, 0, 0. That's the only one that didn't change. And it was the same invariant point for both new functions. Okay, so that's something that familiar we've seen. I gave you a specific function, x squared. But remember, this can apply to any function. I don't know what the equation of this function is. I don't know what the equation of a w-shaped function is. I mean, I can figure it out, but it doesn't matter. All I'm asked to do is take this original one. So remember, this is the fx. And create two new ones. What do the graphs of these ones look like? Just like with the shifts, you can do it one of two ways. You can do it directly on the graph, doing the changes in your head, or you can use mapping notation. So for example, I'll go through the first one and then you guys can go through the second. For this one, if I did it mentally, I would go to all the points I see and double the y values. So I always like to start from left to right on the graph. So I'm going to start at this point. Remember, the x doesn't change. This y value is 4. What's its new y value in 2f of x? 8. So it's going to be up here. This is on the x-axis. Remember, we're stretching above the x-axis. So any point on the x-axis in a vertical stretch doesn't move. In other words, it's an invariant point. This one moves, though. Where does it go? What's the y value here? What's the new y value? 4. This one doesn't move, so it's an invariant point. This one also has a y value of 4, like the one we started with. Its new y value will be 4 times 2, which is 8. And then just sketch the graph. And that's y equals 2f of x. So that's a way, and that's a way to do it mentally using the graph. And it's pretty simple because you're only doing one transformation. But if you're doing several transformations, that's when you might make little mistakes. So if I did mapping notation, I would do it like this. I would say, okay, all the original points are x, y. So I've got -4, 4. And I've got -2, 0.
0, 2, 2, 0, and 4, 4. What's the formula for every new coordinate? Well, the x value doesn't change in a vertical stretch, but the y gets multiplied by whatever this number is. So the formula for every new point is going to be x comma 2y, and then you just convert each point. So you get negative 4 comma 8, negative 2 comma 0 still stays there, 0 comma 4, 2 comma 0, that one stays, 4 comma 8, and then plot all those points and connect them. You'll see you get the same graph. Okay? Whatever way works for you. Because when you get tested on something like this, you really don't get showing work is really not part of the question. Just the final result is part of the question. Because if you did it in your head, you haven't shown any work, but you've done it correctly, so you get full marks. If you do this, great, you're still going to get the same full marks. You're not going to get any more for showing work. So for B, we're going to do half of the red function. Okay, in other words, half of the y values, where the x values stay the same. Once again, you can do it right on the graph in your head by just going to each point and plotting the new image points, or you can use mapping notation. So if we did it in our head using the graph, y value is 4. What's the new y value? Half of 4. Y value is 0. What's half of 0? 0. Y value is 2. What's half of 2? 1. Half of 0 is still 0. Half of the y value 4 is 2. And there's our new function. If we stretch it by a factor of 1/2, this is y equals 1/2 f of x. If you did it by mapping notation, I'm not going to write the whole thing out, but if you're going to call every original coordinate x comma y, what would be a formula for every new coordinate? X doesn't change, comma, half y. And then you would do all your points, list all these, and then list all the new ones by taking half the y's. Invariant points, what are the invariant points for both of these functions? Negative 2, 0 and 2, 0, right. Okay. One more before we go on to horizontal stretches. Here we have another graph. This time 2 transformations are being done to it. Okay, we're combining transformations now. So in this case, it might be helpful to do mapping notation, because what you would have to do if you do it mentally is you're going to have to go, okay, go to every y point, take 2/3 of it, and then add 2. That could get mixed up in your head a little bit. So mapping notation, you can still do it mentally. Okay, I'm not saying you can't. Anyway, what is this? So when we want to come up with the mapping notation formula, so I got to look at all the numbers around the function and tell myself, what transformation does it represent? What does this mean? The 2/3 in front. Vertical or horizontal? vertical. So that means I multiply every y value by 2/3, right? What does this mean? Move up to y values or x values? If I'm moving vertically, y values. So the x values are not changing at all. However, the y values, I have to multiply, space here. I have to multiply every y value by 2/3, and once I have that answer, I have to add 2. So when I get all the new points, the x values are not going to change, but the y values are going to change. I have to take every original y value, multiply it by 2/3, and add 2. So what is 0 times 2/3? Plus 2? Okay. And I would suggest you plot as you go. So -4, 2 is the first problem. We've got to know your fractions here. What is 2/3 of -3? 2/3 of -3 means 2/3 times -3. So you get -6/3, which is -2. Okay. So 2/3 of this is -2, but then I have to add 2. 0. Plot it. Connect. Well, 2/3 of 0 is 0, plus 2 is 2. That's the same as this one. So I get 0, 2. Connect. 2/3 of 3 is 2, plus 2 is 4. And then this is going to work out to 2 again, because 2/3 of 0 is 0, plus 2 is 2. And you get that. So if you did it mentally, you're still going to get the same thing. Like here, the y value is 0, so 2/3 of 0 is 0, and then add 2, so I'm here. This one, take 2/3 of -3, which is -2, which means I'm here, and then move up 2. So you see they all work. Okay? When in doubt, use mapping notation. It's much more accurate, trust me. Any questions about vertical stretches? Okay. Now let's move on to horizontal stretches. This is something new. So now we're pulling from the y-axis or we're pushing in. Okay. So that means any point on the y-axis in a horizontal stretch stays there. If I pull it this way, or if I pull it this way, or if I push it in, or if I push it in. Okay. So notice what happened, like in a vertical stretch, the y values are changing. In a horizontal stretch, the x values are changing, but the y's are not. Okay. So the x values are affected here. The y's stay the same. You okay? Just say it next time. I'm cracking one open. Hop in a cool one. Okay, so let's start with this one again. Now this, you're gonna have to follow closely because it's not as common sensey as you think it would be, but it's mathematically correct. So we are going to graph y equals in parentheses. Notice that's a big difference between the previous one because now the 2 is inside. I multiply the 2 by the x first before I square it, whereas in the other one, I squared it first, then multiplied by 2. So remember, in this one, the y values, the x values change, the y values do not. When we stretch horizontally. Okay. Y equals x squared, that's the f of x, specific f of x. Now, what value, what negative value, because the original one's negative, is so on the left side, do I plug in here so that when I times it by 2 and then square it, I get 4. What negative value do I plug in here that when I times it by 2 and square it, I get 4? Negative 1. What negative value, because I'm on the negatives of the axis, do I plug in here that when I times it by 2 and square it, I get 1? I can't hear. I mean, I heard some sounds. No? What value? Negative value. Negative a half, right? Okay. Because remember I said it had to be a negative value. This whole thing has to work out to 1, doesn't it? Because 1 squared has to give me 1. So 2 times what is negative 1? That's negative a half. This is a little easier. What value do I plug in here so that when I times it by 2 and square it, I get 0? 0. If you notice, now we're on positive 1 and positive 2. It's going to be the same as I did in the negatives. So 2 times 1/2 is 1. 1 squared is 1. 2 times 1 is 2. Squared is 4. So I get that. What happens to every x value? I times every x value by what? A half. So if the number in front was 2 of the x, but inside the function, remember it's not outside the function, it's inside, okay? In order to find the new x coordinates, I have to multiply by the reciprocal of whatever that number is. What's the flip of 2? 1/2. Okay? So what's the formula here? I have to multiply every x value by 1/2. The y values don't change in a horizontal stretch. So therefore, if we graph this, we get negative 1, 4, negative a half, 1, 0, 0, half 1, 2, whatever, wait a minute, 1, 4. So the bigger the number it is inside the function in front of the x, the more compressed it's going to be when you stretch it horizontally. So this is y equals 2x in parentheses all squared. So therefore, in y equals in parentheses 2x all squared, each x value is half. And that's the reciprocal. We're going to find that works every time. And we call it a horizontal stretch by a factor of 1/2. So even though it says 2 in the equation, it's 1/2 the actual stretch. So what do you think now is going to happen when it's 1/2 inside but in front of the x? Every x value is going to get multiplied by 2, the reciprocal. So every x value is doubled. And we call this a horizontal stretch by a factor of 2. So when you do horizontal stretches, you got to think reciprocals when you actually do the graph or actually do the mapping notation. So again, reciprocal. And we'll see that's how it works again. This doesn't change. So 4, 1, 0, 1, 4. Well, what negative number that when I multiply it by 1/2 and then square it will give me 4? -4, right? No, wait a minute. All right. Yeah, -4. Because 1/2 times -4 is -2. -2 all squared is 4, is what I'm looking for. What negative number do I plug in here so that when I multiply it by 1/2 and then square it, I get 1? -2. Notice the relationship. If the original x is -2, the new one in 1/2 is times 2. Times 2. Times 2. Times 2. Times 2. So the mapping notation formula for 1/2 x together all squared would actually be 2x on the 1. And here's what it looked like on the graph. So this one stays the same. The original one now becomes -4, 4. This one becomes -2, 1, 0, 0, 2, 1, and 4, 4. That's y equals 1/2 x all squared. When stuff is inside with the function, it seems like the opposite things are happening, right? Like remember when we did shifts, if it was plus, we moved left. It was kind of opposite thinking. It's kind of opposite thinking with stretches too. There's a number in front. You think, oh, you would times it by 2. No, you times it by the flip of 2. Okay, let's do a couple of questions, a couple of examples. So we're back to this one. The W again. I don't know the specific value of the, or I don't know the specific equation, so I'm just calling that y equals f of x. Again, you can do it in your head and on the graph, or you can do it using mapping notation. So I'll do the same thing. So if we use mapping notation, hello. Staying excited over that. So if there's a 2 inside getting multiplied by the x, or get, okay, that means y is not affected. But the x is getting multiplied by half of 2. There's half, not half of 2. So that means every new one would be -2, 4, 1, 0. That stays at 0, 2. That becomes 1, 0. That becomes 2, 4. Plot all those points. So we get -2, 4, 1, 0, 0, 2, 1, 0 again, and 2, 4. And it looks like that. So notice, even though it's 2 in the equation, when we do the actual horizontal stretch, it compresses. So this is y equals f of 2x. And again, we could have done it mentally. So take every x value and half it. So go here, half of -4 is -2. Half of -2 is -1. Half of 0 is still 0, which makes sense because we're stretching about the y-axis. Half of 2 is 1, half of 4 is 2. Either way works, okay? So in y equals f of 1/2 x, is the 1/2 going to affect the x coordinates or the y coordinates? This is what you got to ask yourself when you see questions like this. So if it's inside the function, it always affects x. If it's outside the function, it always affects y. Like if you think about it, when we did ones like this, if it was outside, that's a vertical stretch, it affects y. If we had something at the end of the function, that's a vertical shift. It affects y. But anything inside, so if you have this, let's say we got a 2, and then we got in parentheses x minus 4, everything's affecting x because it's inside the function. This is a horizontal stretch. This is a horizontal shift. Okay, that's what we're eventually going to get to. So in a half x, if we did mapping notation, every original point we call x, y, but every new coordinate, what will its formula be? Yeah.
The second point, like how it's 2 zeros, then I'll go to -2 zeros.
Oh, sorry, -2, 0, and then -1, 0. Yes. Forgot the negative sign. Yeah. What's the formula for the new point? 2x, comma 1. And then you can list the points and use mapping notation, or you can do it in your head. Here, the x value is -4. Its new one becomes -8. Here, The original x value is -2, the new one is -4. Here, the original x value is 0, the new x value stays where it is. Here, the original x value is 2, the new one becomes 4. Here, the original x value is 4, the new one becomes 8. So notice the bigger the number inside the function in front of the x, the narrower the stretch. It's the opposite of what's happening. Okay, so this is y equals f of 1/2 x. What were the invariant points for both functions? It's actually the same for both functions.
0,
0, 2. That one never changed. Okay. This one. This one, you got to figure out what the stretch is. And then you've got to put that into the equation in correct form. So we're starting with f of x. So we're starting with the red one. That's the original. I want an equation for the new one, g of x. So that means g of x means I'm doing something to f of x. Did I do a vertical stretch or a horizontal stretch? It should be obvious that it's horizontal, and it came in, didn't it? What's the original x? I'll go to the positives. What's the original x point here? 6. What's the new corresponding x point? 2. What do I multiply to get from 6 to 2? Remember, if you multiply something and you're getting smaller, it's got to be a fraction. 1/3. So from here to here, I times 1/3. And that actually works here to here too, doesn't it? This x value is -6. -6 times 1/3 is -2. So it works for all the points. Okay? But if I times 1/3 in the horizontal stretch, what number goes in the equation? 3. So we don't write 1/3, we write 3. So it's going to be f of 3 of x. The stretch, the horizontal stretch is 1/3, but when you put it in the equation, you got to flip it before you put it in. Because remember, if it's 3 in here, then we flip it to get the actual horizontal stretch. What if we work the other way? What if this was our starting function, g of x, the blue one, and f of x was our new one? What would I do to function g? Multiply by 1/3? What's the original x here? What's the original x here? What did I multiply to get from 2 to 6? So I times 3. So if I times 3 in the actual stretch, what number goes in the equation? 1/3. And remember, it's g. So it's g of 1/3 of x. I know it's a little hard to wrap your head around at first, but you'll get used to it. Okay. Any invariant points in either of these? 0, 4. It didn't matter which direction we went, from f of x to g of x or g of x to f of x. This one never changed. Okay. This is summarize, like I did before. Did I miss something? I don't think so, did I? Sometimes this smartboard gets a little wonky on me. No, I didn't miss it. If there is a number in front being multiplied by the function, and we always refer to it by the letter a, That is a vertical stretch. Remember, we don't, if there's a negative A, the negative means something else. That's why I do absolute value. I am only worried about the positive, if this, the positive part of A. If it's bigger than 0, then we multiply everything by A. If it's between 0 and 1, then we multiply everything by whatever fraction it is. So there's a vertical stretch by a factor of A. Not including any negatives. That's why I take the absolute value to get rid of any negatives. That's the third transformation we're going to do. If there's a number in front getting multiplied by the x, if there's a number inside the function getting multiplied by the x, that is a horizontal stretch. Regardless of whether b is bigger than 0 without the negative, or it's a fraction between 0 and 1, it's always a horizontal stretch by a factor of, can you tell me? If it's b, then the stretch is a factor of 1 over b. No negatives, so I'm going to put an absolute value. Excellent. Okay. Question.